Hello everyone, welcome to lecture 13. Well, in this lecture we will learn about quadratic functions, and we will study different behaviors of graphs of quadratic functions because this is the smallest polynomial function which we will cover in the next lecture. Okay, so we have seen different types of functions in the previous lectures. For example, we have a linear function which is given in this form, and we have a quadratic function which is written in this form. So the standard form of a quadratic function f of x is given by ax squared plus bx plus c, and we have a restriction, and that restriction is a has to be different from 0. Okay, we don't care about b and c, they could be 0, but a has to be different from 0, because if this is 0, then we don't have this term. That means, because if a is 0, a times x squared is 0, so what we are left with is only this one. And if we are left with this one, it's not a quadratic function anymore, it's a linear function. Okay, so in order f to be quadratic, a has to be different from 0. That's why we put this restriction. So for a quadratic function, based on the leading term, based on the coefficient of the leading term, which is a, we can determine whether the function opens upwards or downwards. The graph of the function, I mean. Okay, because the graph of a quadratic function is always a parabola. If we have a function something like this, it doesn't matter what a is, what b is, what c is, it's always a parabola, and that parabola either will open upward or downward. Okay, you may say, how about to the right or to the left? Well, this cannot happen, because if it opens to the left or to the right, then this is not a function anymore. Remember, using the vertical line test, if it crosses the function, the graph of the function at more than one point, then we don't call this a function anymore. Okay, but these two they are functions. So if we have a function, we know it's a function, and that function is given by this form, and the graph of this of such function opens either upward or downward. And how do we know that? Without graphing, I mean. If you graph it, then there is no question about that. But without graphing, we can determine whether the graph opens upwards or downwards, and that's based on a. So if the graph opens upward, that means a is positive number. If the coefficient of this x squared is a positive number, we don't care how big it is, but if it is positive, then the graph will open upward. If a is less than 0, then the graph opens downwards. Okay, so this is very helpful information. Just without graphing, by just looking at the coefficient, we know whether it opens upward or downward. So for example, we have f of x equals to x squared. The graph will open upward like this because the coefficient is positive 1. And for f of x equals to negative x squared, the graph opens downward like this, because in this case a is negative 1, which is less than 0. Okay, here our a is greater than a is positive 1. And as you may notice here, there is a vertex. This is what we call the vertex. The turning point is called vertex. Okay, for example, for this one the vertex is here, and for this one the vertex is here. Now, how do we know the vertex? If you have the function f of x equals to ax squared plus bx plus c, how do we figure out what the vertex is? Okay, without graphing the function, we can figure out what the vertex of that graph will be or is. Okay, and that is by rewriting this function in its vertex form. So the standard form of a function is this one. This is what we call the standard. And then I can rewrite f of x as a times x minus h, where h is some real number, plus k. And this is what we call the vertex form. Okay, so if I can write f in this form, well, then the vertex is just the point h comma k. Okay, simply this point at this point right here, or this point right here, is given by h comma k, and those h and k are the values which we have right in here. Okay, this is h and this is k. But the question is, how do we change from standard form to vertex form? If I'm given any function, how can I rewrite it into vertex form? Well, that's by completing the square. Remember, we use this technique to solve a quadratic equation, and we use it now to rewrite a function into in a vertex form, and we will see an example how to do that. Okay, now once we have this, once we have the vertex form, then we can, well, let's look at this graph now. We can study all the behaviors now. So as I mentioned earlier, the vertex is given by h comma k. H is the x value and k is the y value of that point. So the coordinate, I mean not values, but the coordinates, the x coordinate is h and the y coordinate is k. So this point is h comma k, and that point is the minimum point of this if the graph opens upward. So in this case, what does that mean? A is positive. So when A is positive, then we have a minimum point at the vertex, because the graph opens upward, which means all the other values are greater than this value, which means the y values, we are looking at the y values because the function value basically means the y value. Okay, the x value is horizontal, so the y value, we are looking at the y value. So the minimum y value is at this point when A is greater than 0. So the point as a point, we call it minimum point, and minimum value is the y value at the minimum point, which means the minimum value is k itself. Okay, so when you're asked a value, you pick k, the y value, or the y coordinate of that point. When you're asked the minimum point of that graph, then it's the vertex when the graph opens upward. And when the graph opens downward, the vertex becomes maximum point, and the y coordinate k becomes the maximum value. Okay, and in this case, a is less than 0. Okay, so suppose we have, well, we have this already written in vertex form. This is already vertex form, so we don't need to rewrite it. So we have f of x equals to negative x plus 2 the whole squared plus 4. We are asked to determine whether the graph opens upwards or downwards. Now, to determine this, what do we need? We need to know what our A is. Okay, we just look at the coefficient of the first term, and that's given by this value. So in this case, our A is -1, which is less than 0. Therefore, the graph opens downwards. Okay, just by looking at this, I can say the graph opens downwards. And then identify the vertex. And for this one, let me rewrite it. Minus x plus 2 squared plus 4. Well, if you notice here, it's not exactly the same as we saw earlier up there, because here it was negative, now it's positive. So can I rewrite this one in the same way what we have up there? Well, yes. So let's rewrite this one. This is negative x plus means minus 2. Okay, this is basically x plus 2, but I rewrote it this way so that we can understand what's going on. Plus 4. Now, what is my h? This is my h. This is my k. Okay, therefore, h comma k is just -2, 4. So be careful. Just by once you have this one, don't say this h is +2, because this has to be minus x minus some value. So you have to somehow rewrite this one. So the trick is when the inside part, instead of rewriting like this, once you understand it, then you don't need to rewrite it this way. So what we do is, if this is plus, if the term inside the parenthesis is like x plus 2, for example, like this one, then take the negative of this. Okay, well, take the negative of this one. If it is minus, then just take the positive of that one. So always we take the negative of that number inside. Okay, which basically means the opposite of that one. So here we have +2, and I pick -2. Okay, so this is the vertex. And then x-intercept. Well, this basically is we need to solve 0. We substitute f of x by 0, which means the y value, x plus 2 squared plus 4. Now moving this to the right, we get x plus 2 squared and multiplying both sides by negative. I will continue here. It will be +4. Let me rewrite it the other way. I will put this on the left side, equals to +4. Okay, now taking the square root of this, taking the square root of both sides, we will have this one. So this will be just x plus 2, and this is plus or minus 2. Therefore, x is, if we transfer this one to the other side, it will be 2 minus 2, or -2 minus 2. So it will be 0 and -4. Okay. Therefore, x-intercept is at the point 0, 0, and -4, 0. The y value is y 0 at x-intercept. Okay. Okay. And how about the y-intercept? Again, to find the y-intercept, we substitute 0 for x. Therefore, we have f of x, or y equals to -0 plus 2 squared plus 4. And this is -0 plus 2 is 2. 2 squared is 4 plus 4. And this is just 0. Therefore, it is 0, 0. Okay. So as you can see, these are the two. These are the same. So at the same point, it's touching, which means basically at the origin, it's touching the y and the x-axis. Okay. But for the x-axis, there is another one. It touches the x-axis at another point. Okay. Now, based on the information that we have now, can we sketch the graph? So, well, now we have a point, x-intercept and y-intercept at this point. And there is another one, -4. Let's say we have -4 right here. And -4, 0 is here. So it touched the x-axis at these 2 points. And let's find out what the vertex is. Well, we found it already, so it's -2, 4. So -2 is right here, and 4 is somewhere here. Okay. And we know the graph opens downwards, right? Therefore, I can just connect these points and I can have the sketch of the graph. Because I know it opens downwards, and well, it's a parabola, so basically the graph of the quadratic function is more or less okay. So can we figure out, or can we find the axis of symmetry? Well, here the axis of symmetry is not symmetric with respect to the x-axis. It's not symmetric with respect of the y-axis. It's not symmetric with respect to the x-axis, y-axis, or origin. But there is one symmetry, and that is this line. Okay, so what is this line? This is axis of symmetry. And this value, the x value at this point is, this is -2. So this vertical line is given by x equals to -2. And the axis of symmetry is this number, okay? Not this number, this line. X equals negative. This is a graph by itself. Okay, how about the maximum or minimum value? Well, in this case, we have a maximum value because the graph opens downwards, and we know the vertex is at -2, 4. So the maximum value is the y value at the vertex, therefore it's just 4. Okay, so we have a maximum value. And how about the domain? So just look at this graph. Domain means the x values, or you can look at the function, of course, the function itself. But by looking at this graph, if you take this forever, now it's not getting narrow and narrow, it's getting wider and wider. So if we take this forever, what values, does it have any restriction on the x values, like this horizontal values? So we have this x values here, and we have to the right. And this graph, it's going, now I look to the x values corresponding to this graph. So as this graph goes to this direction, the x values are going to the left, right? And similar to the left, and similar on the right side. So there is no restriction on the x values that this function takes. Okay, it can take any x value, any real number. Therefore, the domain of this function, because it's going horizontal and vertical, horizontal to the left and to the right forever, the domain is all real numbers. And how about the range? And to figure out, to determine the range of the graph, you look at the y values that this function covers. So the y value starts from here, and this is 4, and it does not go beyond this one, above this one. It go below this one, okay? So if I go down here, it touches all, or it has, we have a graph corresponding to each and every y value below 4, and 4 is included. Therefore, the range is from -infinity to +4 inclusive. Here we have the domain and range in interval notation. Okay, so this is how this is basically the how we study, or how we can determine all the behaviors of a the graph of a quadratic function. Okay, all right, now we have a quadratic function written in a standard form, and we are asked to write this one in a vertex form. Now, this is the question. Now we have this, and let's say I ask you to rewrite this one in vertex form, but given this function, I can ask you all these questions that we answered up here. And to answer all these questions, particularly most of them, particularly like the vertex and maximum point and so on, we need to change this one to a vertex form. So basically, we have to know how to change this one to the vertex form so that we can answer those questions. Now, we have this, and I wanted to rewrite this one in vertex form. So let's start with, I will use blue pen. Use this. So we have qx equals to 2x squared minus 4x. I will put parentheses here, minus 3. Okay, I separate them. There is no change. I just put parentheses inside. Now, we need to complete, or we need to apply the completing square to this term. Okay, just this inside part. So this becomes qx equals to, let me take out the 2 first, 2x squared minus 4 minus 2x minus 3, 2. Now, how do we complete the square of this one? X squared minus 2x. What we do here is we add half of this term right here, this coefficient, half of it, negative 2 over 2 squared. Okay, and I have to add the same number, negative 2 over 2 squared. So obviously this is 1, but just to make general how we find that 1, I'm doing it step by step. So this is the negative 2, so I take half of negative 2, which is negative 2 over 2, and I added the same, sorry, 1 has to be negative. This is minus. Okay, this is minus. All right, so we close the parentheses and we have our minus 3. Okay, so continuing this, I have 2x squared minus 2x. This is negative 1. Negative 1 squared is positive 1, so plus 1. Now we take this one out. And remember, when you take this one out, you have to multiply by this one because it's inside this parenthesis. Okay, so I wanted to move this one out. And when you move this one out, you have to multiply this. And it becomes, this is plus 1, right? But we have the negative, so it will be negative 1. Negative 1 times 2 is negative 2. We have negative 3 here. Okay, so 2. Now what is this one now? This is a perfect square now, because we used it. We use the completing the square formula or technique. Sorry. So this is basically x minus, what was that, half? Half of negative 2? Half of negative 2 is negative 1. So we have negative 1 squared. Okay, so just to check, what is x minus 1? Oops. X minus 1 squared. This is x minus 1 times x minus 1. And this is, if we distribute this one, we have x squared minus x plus 1, x squared minus 2x plus 1. And this is exactly what we have right here. Okay. Okay. And here we have minus 5. And well, that's it. So we have the vertex form of Q of X. This is the vertex form. And now if we're asked to find the vertex form, the vertex of this the graph, then we can say it's 1, -5. For this negative, we don't have any problem. We just pick that because this is K by itself. So K is -5, but H is always the opposite. If this is negative, pick positive. If this is positive, pick the negative. Okay. Okay. Now, how do we find the vertex in general? Now, instead of changing this one to the vertex form and determining what the vertex of that graph is there a way to figure out the vertex given the function in standard form? Okay, we have f of x equals ax squared plus bx plus c, where a is different from 0. Then the vertex form is given by -b plus 2a. Here we have the x coordinate, -b over 2a, and the y coordinate is f of -b over 2a. Okay, and the derivation for this one is basically what we did over here, and well, that one is basically, okay, let me see. So here we have this f of x. I will just show you the graph. I'm not gonna show you all the things so that you don't get confused. But let's say we have ax squared plus bx plus c. Now let's do the same procedure. Let's complete the square of this one. So this becomes ax squared plus bx plus c. Now divide, take out a, factor out a, then this x squared, and this one, what do we have? This becomes, okay, it becomes b over a x. Okay, this is what we have, plus c. Now we do the completing square for this one, and we have ax squared plus b over ax. Now what do we add here? Half of this one, the square of half of this one, and that is b over 2a squared, and I subtract the same number because it has to be 0 plus c. Okay, and now we move this one out, and when we take this one out, we have to multiply it by this a. So we have a x squared plus b over ax plus b over 2a squared minus a times b squared over square of this one is 4a squared plus c. And what is this? Well, this is x plus half of this is this part, so I put that one here, squared, minus, how about this one? And this is, let's simplify this. We have b squared over 4a plus c. Okay, and well, we are almost there. This is x plus b over 2a minus, now let's rewrite this one, b squared minus plus 4ac over 4a. Okay. This has to be plus. If we factor out, no. If we factor out minus here, that becomes, well, I don't need to factor it out, so just let me keep it out that way. We can keep it that way. We don't need this parentheses. Okay, so we have this one. Now, what is the vertex from this? The vertex from this is the x coordinate, obviously, is this one, negative b over 2a. And the y coordinate is negative b squared plus 4ac over 4a. Right? So either we write it this way. This is what we have right here. This is the x coordinate. And instead of writing this one as k, you can say just f of b plus 2a. Okay, f of b plus 2a will give you this one. If you substitute b plus 2a, then that becomes, sorry, negative b over 2a. If we plug negative b over 2a here, this becomes 0. So we are left with this one. And that's basically what we have. This is f of negative b over. So in general, without converting this into vertex form, we can use this formula or this notation or this coordinate to find the vertex of a quadratic function. Okay. So last time we studied the discriminant of a quadratic function to find or to determine how many real numbers, how many real solutions it has, and how many complex solutions it has. Okay. And today we will use this discriminant to figure out or to determine how many x-intercepts it has, because basically the x-intercept is the solution to the function. So it's the same idea. Therefore, now if we have the determinant, or if the determinant, this discriminant is 0, then the graph will have only one x-intercept, which means the graph of f of x will touch the x-axis at only one point. If the discriminant is greater than 0, then we will have two x-intercepts. It touches the x-axis at two different points. And if the discriminant is less than 0, then it doesn't touch the x-axis, okay? Which means there is no x-intercept. Therefore, using the discriminant, we can add another information. We know, if you know this one, then you can, again, this can help us to plot or to graph or to sketch the graph of the function, okay? And the next is polynomial functions. Well, polynomial function is more general, but it's a continuation of quadratic function. Of course, quadratic function is a polynomial function, but not all polynomial functions are quadratic, okay? So quadratic is a small or a part of this polynomial function. A polynomial function is written in this form, and f of x equals a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, and so on and so forth. But in polynomial function, the most important one is this leading term. We call it leading term. So this polynomial function, by looking at this power, the power, we call it n is an integer, and this coefficients, these ai's, a1 up to an, sorry, a0, not a1, a0 up to an, all of them, the coefficients are, they have to be real numbers because we are only dealing with real numbers. And the leading coefficient has to be different from 0, just for the same reason that we explained for the quadratic equations. So such polynomial, we call it polynomial function of degree n, whatever n is, okay? N is any integer. Okay. Well, it should be positive integer, actually, not any integer, it should be positive integer. And the domain of a polynomial is all real numbers, because if you look at this, there is no restriction. We can plug any value to x, any real number, Okay, there is no restriction. We don't have any problem because the output will still be a real number. Therefore, the domain is all real numbers. And another property of a polynomial function, the graph of the polynomial function is always continuous and it's smooth. Smooth means if you can draw the graph without lifting the point, the pen. For example, this is continuous. Okay, as you can see, I haven't lifted it. If there is a sharp edge, of course, I don't lift it, but if there's a sharp edge, then this is not continuous at this point. Okay. If there is break, then again, that's not continuous. Okay. So the graph of a polynomial, as we can see from this one, no, this is, sorry, I said this is not continuous, but this is not smooth. This is not smooth. Of course, it's continuous, but not smooth. So it has to be smooth, and it has to be continuous for a graph of a polynomial. This one is not continuous because we have a break here. Okay. Of course, it's not continuous and it's not smooth, but something like this is smooth and it's continuous. Therefore, graph of a polynomial satisfies both of them. Now, based on the leading term, we can determine the behaviors of the end behaviors of the graph of a polynomial. End behaviors, we mean by the end sides of the graph. We don't know anything about the middle, but the end part we can determine what it looks like. And let's see what we mean by this. So suppose, let's say n is even. N is the power of the leading term or the power of the polynomial itself. N is even, and the leading coefficient an is positive, greater than 0. And if the leading is greater than 0, we know the graph opens upwards. Now here I use the ... because I don't know anything about this area, about this, about the behavior of the graph inside here in the middle, but the end part I know it. Therefore, if n is greater than 0 and if n is positive, is even, then we have this as x goes to negative infinity, which means as x goes to the negative infinity here, the graph goes to positive infinity, which means it's opening upwards. And as x goes to the positive infinity, then the graph again goes to positive infinity. So both the arrows or both the endpoints are going upwards. So the end behavior here, the left side is going up left, and the right side is going up right, which means this one. Okay. And the other case is n is still even, but a sub n is less than 0. It's negative. In this case, this is very similar to the quadratic equation or graph of quadratic equation. Since it's negative, the graph or it opens kind of downward. So the endpoint, they go downward, both sides. So we say as x goes to negative infinity, f of x is going to the negative infinity because it's going down, and down the y value is negative. So we have down left, okay, because the left side is going down. And the right side, as x goes to positive infinity, x is going to the right, which means positive values, but the graph is still going down, which means down right, okay? It's going this direction. So based on this two information, I can determine the endpoints. And the other one is when n is odd now. For example, if n is, let's say 1, 3, 5, 7, and so on. Here when n is 2, 4, 6, and so on. And now here, when n is odd and a sub n greater than 0. In this case, we have the graph, which looks like this one. So as x goes to negative infinity, the graph of f of x goes to negative infinity. Okay, it's going downward. And as x goes to positive infinity, the graph goes to positive infinity, which means it's going up. So here they go opposite side. When n is odd, it's always opposite. They don't go to the same direction. But when n is even, they go to the same direction, either both down or both up. So here we have down left and up right. And this is the opposite. If if the leading coefficient is less than 0, then we have, as x goes to negative infinity, f of x goes to positive infinity, and the opposite. So we have up left and down right. This is down right. Okay. Therefore, again, just by knowing an and n, we can determine the end behaviors of the graph of f of x. Okay. Okay. So for today, I'm going to stop right here, and next we will start, or we will learn how to identify zeros and their multiplities of polynomial function. Okay. All right. So see you in the next lecture.